Hello, good day, wherever you're watching from. Welcome back one more time to my YouTube channel. Today we are continuing on our series of capacitor and capacitance. Today we'll be looking at parallel plate capacitors. So let's just have a brief interactive session before we look at some few examples. So let's assume these are two plates in parallel, and we can call this our terminal, as we discussed in our previous class. If you have not watched our previous class, you can just go back and watch so that you would have a better understanding of what we're doing here. So we say for a parallel plate capacitor, capacitance C is proportional to the area the area of this plate A of the plate, inversely proportional to the plate spacing, the spacing between these two plates, the spacing here, spacing here, spacing here, spacing D, and it also depends on the nature of the dielectric. So it also depends on the nature of the dielectric that it's in between these two plates of the capacitor. Alright, so let's now say capacitance C. Remember, we are now having area. In this scenario, we are now considering the area A. This is permittivity of free space, this is relative permittivity, this is area, and this is our dielectric. So we say our E naught is a constant. That's permittivity of free space 8.85 multiplied by 10 raised to the power of minus 12 farads per meter, and our E at R is relative permittivity, A is area of one plate in the meter square. Area of each of this plate is A in the meter square, and D is the thickness of the dielectric in meter. So when several plates, when we now have multiple plates, this is 2, we have multiple, it can be 2, 3, 4, 5, 6, 7, 8, up to 20 plates. We can note each plate as N. We say several plates which we note as N now forms a capacitor. Then capacitance is inversely proportional to N minus 1. So what it means here is that when we have several plates noted as N, when we have several plates forming a capacitor, multiple plates, let's say this way, I have multiple of them, multiple plates, okay, forming a capacitor, multiple plates, let's say positive, this is a negative, let's say polarized, and every distance separated here is dielectric. So we have multiple plates. The capacitance now C is inversely proportional to what? N minus 1. So capacitance now, let's say capacitance C is equal to what? E naught A R open bracket N minus 1, all measured in what? Farads. So this is a case scenario where we're finding the capacitance of a capacitor which have a multiple plates. So to find the number of plates is just N minus 1. When you're given 19, let's say N is equals to 19, let's say A C is equals to, given then you have the constant, multiplied by ER depending on what you're given, and 19 minus 1, then your C capacitance will now be the value of E naught multiplied by the value of ER multiplied by now 18. Hope you understand what I'm driving at. So let's now proceed to an example. The question now says a ceramic capacitor has an effective plate area of 4 centimeters square separated by 0.1 millimeter of ceramic of relative permittivity 100. Calculate the capacitance of the capacitor in picofarads. And B says if the capacitor in part A is given a charge of 1.2 microcoulombs, what will be the potential difference between the plates? So let's now say solution. Let's now say solution. Solution area A is equal to 4 centimeters squared, which is equal to 4 times, in meter now we have 4 times minus 4 meter square. And remember the dielectric was 0.1 millimeter, the same thing as 0.1 times 10 raised to the power minus 3 meter, and our constant is 8.85 by 10 raised to the power minus 12 farads per meter. And then lastly our ER is 100. So capacitance now of this capacitor will be equal to capacitance C is equal to E naught ER, as we've stated, A all over B farad. So we now say C is equal to 8.85 multiplied by 10 minus 12 times 100 times 4 times 10 minus 4, and all in farads. That's our unit. Now have 0.1 times 10 minus 3. So C now is equals to 885 times all over by 10 farad, where C is equal to now 8.85 times 4 times 12 all over 10. If you agree with me, you can continue with me, but if you don't agree, you can verify what I'm doing. Now C final answer will be 354 picofarads. So let's now solve for B. We have now solved for A. We have now solved for A. So let's solve for B and C. B. Question B says that if the capacitor in part A is given a charge of 1.2 microcoulombs, what is the potential difference between the plates? The potential difference between the plates. So we know Q is equals to CV, right? Q is equals to CV, right? So V now will be equals to Q all over C. So remember, our charge was given as what, 1.2 times 10 raised to the power minus 6 all over. Our charge was given as 3,540 multiplied by 10 minus 12 V. So dividing that, you have V is equals to what? 339 volts. 339 volts. That's our final answer. So let's now look at another example briefly. So this is our second question. It says a wax paper capacitor has two parallel plates, each of effective area 800 centimeters squared. This is 800 centimeters squared, full stop. If the capacitor, or rather if the capacitance of the capacitor is 4425 picofarads, determine the effective thickness of the paper if its relative permittivity is 2.5. So let's solve. Solution. First thing that we would do is bring out our parameters. We have area 800 centimeter squared, which is equals to 800 multiplied by 10 minus 4 meter squared, is equals to 0.08 meter squared. You can check out the conversion, which will say now C is equal to 4425 picofarads. And similarly, we can say is 4425 to the 10 raised to the power minus 12 farads. Pico is 10 raised to the power minus 12. You can check our previous video on prefix. You would see that that's right. And then our permittivity of free space is 8.85, as always stated, times 10 raised to the power minus 12 farads per meter. And lastly, our relative permittivity is 2.5. Having known that, you now say, let's remember that C is equal to E naught ERA all over D. So the effective thickness, we are looking for the effective thickness, rather the dielectric. So that means we'll make D the subject. So D now is equal to E naught ERA all over what? C. So having done that, we'll now have D, we'll substitute 8.85 times 10 raised to the power minus 12 times 2.5 relative permittivity, and time is our area, which we calculate as 0.08 all over capacitance. We got it as 4.425 times 10 raised to the power minus 12. So now D is equal to, punching it into calculator now, gives us 0.004 meter. Hence thickness D is equals to 0. We can now say 0.4 millimeter. Let's convert it to millimeter. 0.4 millimeter, something as 0.004 meter. So that's that for this